All right, welcome everyone to the second to last visitor this academic year. Next week we will have Patricia Palacios from the University of Salzburg, and she will be doing the usual Wednesday, Thursday talk and seminar as well. This week we have Giovanni Valente from the Politecnico di Milano. He's in the Department of Mathematics. Associate Professor for Logic and Methodology and Philosophy of Science, or
Logic and Philosophy of Science.
Logic and Philosophy of Science, yes. And also the Lisa Meitner Fellow at the University of Salzburg in Austria for 2 years, I think, this project is running. Before, he was an assistant professor of philosophy at the University of Pittsburgh. Giovanni did his MA degree in philosophy at the University of Padua. After which he moved to the United States to do a PhD at the University of Maryland in College Park. He works in philosophy of physics generally, philosophy of the mathematical sciences, with also interest and competence in philosophy of science generally, and in philosophy of space and time, and science and public policy. He has published numerous articles. The last one came out literally a few days ago, I think, in Synthese, and he will be presenting that tomorrow in the seminar. We'll be discussing that work tomorrow. He has a book in Italian on relativistic causality, I think philosophical questions at the intersection of quantum physics and relativity, or special relativity. And he has also won a number of grants. Maybe the other thing, apart from the Wigner Fellowship, that I should mention is the Humboldt Fellowship you had a few years ago at the University of Munich, the LMU, the Ludwig Maximilian University in Munich. Without further ado, let me hand over to Giovanni, who will be talking today about spontaneous symmetry breaking and physical inequivalence, the case of quantum statistical mechanics. Please, Giovanni.
Thank you, Chris. Thank you, everybody, for being here. It's an honor to speak in front of you today. And what I will talk about, as the title that Chris already read suggests, is some recent work that I've been doing on quantum symmetry breaking. And today I will focus in particular on a case study that is that of quantum phase transitions. So let me first state what the problem that I will deal with today is in an informal way. Well, in general, symmetry is characterized by the invariance of certain properties under a given group of transformations. And the idea is that the transform description of the system under investigation should be regarded as physically equivalent to the original untransformed description. There are, however, cases of broken symmetries, and in a broken symmetry, some empirically relevant aspect of the description of the system does not remain invariant under the transformation. And examples of spontaneous symmetry breaking occur in infinite quantum theory. So the question is, put informally, whether descriptions that are connected by a broken symmetry are physically equivalent or physically inequivalent with each other. And throughout the talk, I will try to make this question more precise and to provide an answer, especially in a particular case study of spontaneous symmetry breaking in infinite quantum theory, which is the spontaneous magnetization of a ferromagnet. So in order to do so, I will proceed as follows. I will start by providing mathematical definition of symmetry and to characterize what we mean by symmetry. Breaking, I will describe what is spontaneous magnetization of a ferromagnet, in particular the spontaneous magnetization of an infinite spins chain, and then I will outline and address a dilemma concerning symmetry breaking that has been raised by a philosopher, Dave Baker, in a 2011 article and some follow-up papers, especially one that he brought together with Ann Salverson. And in particular, the dilemma concerns the relation between symmetry and unitary equivalence. So I will discuss this point, and then I will also discuss the related point of how the notion of physical equivalence is related to the notion of unitary equivalence. And then I will focus on the question whether the presence of a symmetry entails physical equivalence, which is actually the claim that Baker puts forward, and I will resist this conclusion, particularly arguing that we can have a symmetry without physical equivalence, and that's the case specifically of the spontaneous magnetization of a ferromagnet. In fact, at the end of the paper, at the end of the talk, I will offer reasons why the different thermodynamical phases of a ferromagnet must be considered, Baker, physically inequivalent. Okay? So let me start out by giving you some background notions. The mathematical results that I will present and discuss are cast in the so-called algebraic approach to physical theories. If you're not familiar with this approach, don't worry, I'll try to explain the meaning of the terms without digging too much into them. And I will illustrate the significance of the formalism, at least the part of the formalism that is relevant to the topic or to the issue at stake with the aid of pictures. Okay? So in the algebraic approach to physical theories, physical systems are described by means of algebras of observables, namely physical quantities such as spin, position, momentum, that one can actually measure or observe. And in particular, throughout the talk, when you see the symbol curly A, I will denote a von Neumann algebra of observables. All the results that I will state are true for von Neumann algebras, but you don't really need to know the details of von Neumann algebras in order to grasp them. I will represent the set of states, or defined over the algebra, by S A, and I will assume that all the states are normal, namely they are completely additive, countably additive probability states. Okay, now if you take a state over the algebra, well, a state omega, this state induces the so-called GNS representation, which is a triple comprising a separable Hilbert space, as in standard quantum mechanics. The Hilbert space being denoted by H. Big omega will be a vector state in this Hilbert space, and pi denotes the representation of the algebra, and it's such that pi of A coincide with the algebra of bounded operators defined over the underlying Hilbert space. And we refer to the state induced omega inducing the GNS representation as the ground state. And depending on the particular theory we're considering, the ground state will be the vacuum or a thermodynamical phase. Okay? This ground state omega can correspond, based on the GNS representation, to this expression. So it can be expressed as the inner product between omega, big omega, and pi x acting on omega. And that is true for all the elements of the algebra. And the vectors determined by the action of pi x for each x on the vector state omega form a dense set in the Hilbert space. Another concept that sometimes will appear in the slides is that of the affiliated algebra, which is just a double commutant of pi a, which is the weak operator closure of pi a. Out of the technicalities, this means that the affiliated algebra comprises all the elements of pi a plus the weak closure of sequences of these elements. Okay? And sometimes, in order to define physical observables, we actually need to sit in the affiliated algebra rather than on the original algebra or its representation. This is not working anymore. Well, then I'll do this. Okay. Now we can give the algebraic definition of a symmetry, which is really intended as the composition of two bijections. An automorphism, actually a star automorphism alpha on the algebra A, and then at the level of states, we have another map, alpha bar, which is such that alpha bar of the state omega is equal to the composition of omega and alpha to the minus 1. Okay, and you can easily persuade yourself that this definition of symmetries is such that all expectation values are preserved. In fact, if you apply this definition of alpha bar here, you get back immediately omega x. Okay? Now, again, this doesn't work. So when we have a symmetry in place, it actually induces two representations, let's call them pi and pi prime, that are associated with the original state omega, okay, and that's pi, and the transformed state under the symmetry omega prime. Okay, so let's try to understand these definitions a bit more with the help of a picture. Here we got our algebra as a set of observables. The symmetry will map an element x of the algebra onto another element of the algebra pi x, and this induces two representations, the representation pi and the representation pi prime. On this basis, we can now start making the question I raised at the beginning of the talk more precise. The question about physical equivalence or physical inequivalence is whether these two representations corresponding to the original state and the transformed state, so are they physically equivalent or are they physically inequivalent? Okay? And we will have more to add in the talk in order to make this question and the answer even more precise. Okay? Now, an important concept to keep in mind when dealing with quantum probabilities is that of Wigner's theorem. Wigner's theorem establishes that any quantum symmetry, alpha, is implemented by a unitary operator, W, that maps from the original Hilbert space onto the transformed Hilbert space H prime. And it is such that it preserves the linear product. So if you take two vectors in H, okay, psi and phi. Psi prime is defined by W psi, phi prime is defined by W phi. And so if you plug these expressions here, given that W is a unitary, you obtain the equality between the inner products of the two vectors. Okay? And the unitary operator W is called Wigner unitary. Now, given that in quantum mechanics, the empirical content of the theory is partly captured by, at least partly captured by transition probabilities, and transition probabilities depend on the inner product between vectors, the justifications for Wigner's theorem is that a symmetry preserves the empirical the transition probabilities, and therefore the empirical content, or at least part of it, as we will see. Okay, so now it's time to distinguish between unbroken and broken symmetries. We say that a symmetry is unbroken if the ground state is preserved, that is, the original state is equal to the transformed state. More to the point, a symmetry alpha is unbroken if it is an inner automorphism of the algebra, that is, there is a unitary U being an element of the algebra, such that for all x in A, alpha x is equal to U star x U. Equivalently, this means that alpha is unitarily implementable in omega, in the sense that there is a unitary, the Wigner unitary W, such that pi x is mapped onto the corresponding pi prime x by the action of the Wigner unitary. And we say in this case that pi and pi prime are unitarily equivalent representations.
So these are three equivalent conditions?
Yeah, you can show that, at least for pure states, that they are equivalent. Okay. And the key point to retain is actually this: when symmetry is unbroken, pi and pi prime are unitarily equivalent, exactly because there exists a unitary operator that maps pointwise from one to the other. Okay? So in fact, this, remember, must be true for all x. So pi x is mapped into pi prime x. It's important that it's always x the argument. Okay? By contrast, a broken symmetry is a symmetry in which the ground state does not remain invariant, so omega is not equal to omega prime. And so the previous definitions do not hold. So alpha is not an inner automorphism and is not unitarily implementable in omega. There will be some x for which this relation fails. And we say that pi and pi prime, therefore, are not unitarily equivalent representations. An example of broken symmetry is the spontaneous magnetization of a ferromagnet. In this case, will be represented by a quantum spin chain. So consider a sequence, a string of spin systems aligned along the, say, the z-axis and labeled by the integers. Okay? These systems can be spin systems. The z direction can be either oriented up or down. Okay? Now, particularly focus on the so-called Weiss-Ising model for ferromagnetism. And here, to each quantum spin and site K, we associate Pauli matrix and the corresponding algebra, the Pauli matrix sigma z K, and the corresponding algebra describing the system is the algebra A K, which is isomorphic to the algebra of 2 by 2 complex matrices. This is again standard quantum mechanics. And for every finite string, lambda, the overall algebra is defined as a tensor product of all the individual algebras. And to this algebra there is associated an Hamiltonian telling us how the system evolved in the course of time. And the Hamiltonian depends on, in particular, on two terms. B sigma k, which tells us which is the molecular average magnetic field, depending on how each spin system interact with each other. The various spin systems interacts with each other. And the term B, which denotes the homogeneous external magnetic field, parallel to the z-axis. And a somewhat surprising phenomenon is that of symmetry breaking, in which even if there is no external magnetic field, and so B is equal to 0, above a critical inverse temperature, denoted by beta C, all the spins turn up or they all turn down. And that happens spontaneously in the sense that there is no magnetic field inducing the phenomenon. So in particular, if we define the magnetization observable in this way, okay, it will either take the value +1 if all the spins are up, or -1 if all the spins are down. Okay? So just to go back to the picture, even if there is no magnetic field acting on the system, we will observe that all the spins will align in the up direction, so they spontaneously can also flip in the opposite directions. So this is a well-known and yet surprising phenomenon. However, in order to account for it mathematically, in a mathematically rigorous way, we need to take the limit for which the spin chain is infinite. Otherwise, we'll not be able to describe the phenomenon. Let's consider a state omega, now defined on the so-called quasi-local algebra, which is given by the closure of the union of all the possible finite strings, having a GNS representation denoted by pi b beta, okay, where again beta is the inverse temperature. Okay. And one can construct in this way a magnetization observable, Mc, which is given by the weak limit of the image of the magnetization observable for finite strings under the pi representations. And it turns out that this magnetization observable, which is so rigorously defined, is not actually an element of the quasi-local algebra A, but it is an element of the affiliated algebra A, which is the weak closure of A. Okay. So now in particular, once we define this term, if we let B go to 0, and we consider beta greater than the inverse critical temperature beta C, the magnetization observable has expectation values +1 and -1 in the two ground states. Okay? And the ground states will be omega plus for all the spins up, and omega minus for all the spins down.
So, sorry, what's little w there?
Sorry?
I didn't catch that. Little w up in the formula in the equation?
What is? Oh, the weak. This means weak. Weak limit.
Oh, okay.
Okay.
Oh, okay.
Yeah, sorry. I just said that I shouldn't maybe, but it's, yeah. Good. And so the important thing to note is that these two representations of the states in which all the spins are up, omega plus, and all the spins are down, omega minus, representations which we denote by pi plus and pi minus are unitary inequivalent. In fact, this is a case of symmetry breaking. These two states are connected by the so-called flip-flop symmetry, which I denote by alpha plus minus, which out of the technicality, simply represent a rotation of 180 degrees along an axis perpendicular to the z-axis, where all the spins are aligned. And clearly the symmetry is broken, because if I apply the flip-flop symmetry to omega minus, to omega plus, I get omega minus, and vice versa. If I apply it to omega minus, I get omega plus. So the ground states are not preserved, the symmetry is broken. Okay, so that's enough with the technical the background that we need to know in order to assess the rest of the paper, and we can start doing philosophy. And we start doing philosophy by introducing Baker's dilemma. This is the relevant quote. And Baker writes, the apparent dilemma brings together two separate threads in recent literature. One thread suggests that the existence of a symmetry is a mark of physical equivalence. The second thread suggests that physical equivalence is possible only in presence of unitary equivalence. In the example central to this paper, and focuses on the spontaneous magnetization in infinite spin chain, a symmetry can exist between representations without a unitary equivalence. The conflict here is obvious, he says. And I think it gets a bit more obvious if we do something, a step beyond this quote and cast the dilemma into its logical structure. Actually, the underlying assumption, which I indicate with statement 0, is that a symmetry does not imply unitary equivalence. As we know, in the case of broken symmetries, we can have a symmetry and unitary inequivalence. And then the two threads that Baker identifies in the literature can be captured by this statement. Okay? A symmetry is a mark of physical equivalence. Statement 1, symmetry implies physical equivalence. Second thread suggests that physical equivalence is possible only in presence of unitary equivalence. So unitary equivalence, that's statement 2, is necessary for physical equivalence. Okay? So if we put together statement 1 and 2, we have that a symmetry implies unitary equivalence, and thereby we have the obvious conflict with statement 1. Now Baker also suggests a solution to the dilemma. He says, I think its resolution on reflection is also obvious. The first thread should be pursued at the expense of the second. In infinite quantum theory, as elsewhere, a symmetry should be enough for physical equivalence. So again, to put it into the logical structure, Baker suggests to drop statement 2, to deny it, while maintaining statement 1. That's, or at least that's his suggestion. So, to assess his proposed solution, let's start focusing on what is really the central. So statement 0. And then we address the other two statements to see which one should be dropped. Actually, statement 0 is closely related to a puzzle that was pointed out by John Ehrman in a paper in 2003. And John says a broken symmetry is not unitary implementable, as we learned a few slides ago, i.e. its action is not fully represented by a unitary. But then Ehrman asks, how can this be? Since Wigner's theorem has taught us that a symmetry in Qm is represented by a unitary transformation. So, to understand the puzzle a bit better, let me explain it. If alpha is a broken symmetry, as we know, pi and pi prime are not unitary equivalent, so there is no unitary W that maps pointwise between the two representations. Nevertheless, according to Wigner's theorem, the existence of the Wigner unitary W that implements the symmetry is required in order to preserve the transition probabilities. So there is an apparent problem here. There is a puzzle indeed. And I think the solution of the puzzle is the following. And here I developed the suggestion proposed by Herman himself and also by Baker and Alberson in a subsequent paper. And the idea is that actually for any symmetry alpha, it's true that there is a Wigner unitary implemented transformation, the symmetry. However, its existence does not entail unitary equivalence. It actually just entails a weaker form of unitary equivalence. And let me first give you a sense of what's going on here informally with the pictures, and then add more details. And that's the picture we saw before, okay, depicting a quantum symmetry. Now, if the symmetry is unbroken, and the symmetry is expressed at the level of the algebra, is implemented by a unitary operator U, an element of the algebra. At the level of representations, one can map pointwise from one representation to the other by means of the Wigner unitary. However, if the symmetry is broken, okay, pi x will now be mapped onto pi prime x. E will be mapped onto some other element of pi prime a. In general, okay, well, we could have some elements that are x for which pi x is mapped into pi prime x, but there will be some for which this connection does not hold. The important thing, though, is that W map pi x into some other element inside here. Okay? So you cannot transform pi x, does not transform pi x into some other observable outside the representation of pi prime. Okay? So that's the picture. So let's make it more rigorous. Here's again the definition of unitary equivalence we saw before. And these are conditions that I call W-Unitary Equivalence, according to which there is a unitary W from H onto H prime such that pi A, the whole algebra, will be mapped into pi prime A. But that happens without pi being mapped pointwise to pi prime. In this sense, W-unitary equivalence is weaker than unitary equivalence, thereby the name W, which also comes from W.
In the logical sense, because unitary equivalence implies this, but not this.
Exactly. Yeah, strictly in the logical sense. Now, as a matter of fact, if the symmetry is implemented by the Wigner unitary, pi and pi prime being weakly unitary equivalent is enough to guarantee the preservation of transition probability. So we don't need unitary equivalence, all we need is double unitary equivalence. And this idea is made precise in a theorem which is presented by Baker and Alberson, although honestly it was somewhat not known even before them, but they cast it in an interesting way, and they call it Wigner representation theorem, according to which for any symmetry alpha on the algebra there is a unique Wigner unitary such that omega is transforming on omega prime, and this expression holds. This expression tells us that pi prime is unitary equivalent to pi after alpha to the minus 1. Okay? Does not say that pi prime and pi are unitary equivalent, but that pi prime is unitary equivalent to pi alpha to the minus 1. And the presence of the Wigner unitary assures W unitary equivalence because satisfy these expressions even when unitary equivalence fails. Okay? So the existence and uniqueness of W entails preservation of the transition probabilities even when the symmetry alpha is broken. Now, what I tried to do in the paper was to get a better sense of the content of this theorem by trying to unpack it. So, the symmetry U, the unitary operator U implementing this symmetry, being an element of A, actually extends to a unitary operator U bar from H defined on the Hilbert space H. And if the state omega is pure, then we have that pi U star x U is exactly equal to U bar star pi x U bar for all elements of the algebra, where U bar is just the image of U under pi. Now, if the symmetry is broken, U bar implements a star automorphism over DH in our algebra. And in particular, this expression holds. Pi x is equal, so now remain invariant under the action of U bar. And it follows from this, as you can see here, that omega x is equal to omega alpha x. Why so? Well, this is omega alpha x. Okay? Alpha x, by definition, is U star x U. And now, using this relation, we can pass to the third inequality, because this guy is equal to this. And then, by the fact that U bar implements a star automorphism on BH, so we have this quantity, we can move from this third expression to the fourth, and that's just omega x. Now, by Wigner representation theorem, as we saw before, omega alpha x means omega prime x, and thence omega, as it is expected in the case of unbroken symmetry, is preserved under alpha. This is just an analysis of the content of the theorem. But what is important to keep in mind is that the unitary U bar that intertwines pi and pi prime should not be confused with the Wigner unitary W. In fact, U bar, as we see here, maps H onto itself, whereas W maps H onto a transformable space H prime. And in particular, if the symmetry is unbroken, W turns out to be the identity, simply, which entails this expression. Okay? So this gives a bit more sense of the picture so before. For broken symmetries, we can run the same reasoning as before, except that now U bar does not induce a star automorphism of BH. So we don't have the equality we had before, so the last passage is blocked. So omega x is not equal to omega prime x. Now, in this case, in the case of broken symmetry, W turns out to be different than the identity, it's not trivial. And it transforms pi alpha x into pi prime x without making them equal. Okay? Even though it guarantees, as we saw from Wigner representation theorem, that pi and pi alpha are unitary equivalent. But let me skip this part for now. Maybe we can come back later if you have more questions. Just I don't want to complicate the picture too much. The important point is that in the case of a broken symmetry, pi and pi prime cannot be unitary equivalent, as we learned, but only W unitary equivalent. And that's what resolves Hermann's puzzle. So the symmetry is implemented by a unitary without entailing unitary equivalence, just W unitary equivalence. Okay, and that's again the picture as before, whose meaning should now be more transparent to you. So, we discussed the so-called statement zero, the hidden condition or the non-expressed condition in Baker's quote, where it lies out the dilemma. And let me remind you what the dilemma was. Okay, the dilemma is due to the combination of these two statements. Okay, that lead to a contradiction to statement zero, and Baker's solutions rest on the idea of dropping the second statement. Okay. So now we can assess these two statements and see the comment and try to understand which one should be dropped. And let's begin with the second one. One difficulty in assessing any claim that has to do with physical equivalence is that we first need to understand what we mean by physical equivalence, and there are several proposals in the literature. And notice, by the way, that this case, the assessment of physical equivalence, and so the assessment of these two statements, is more complicated than the assessment of this statement, which can be treated mathematically, simply mathematically. But when we discuss physical equivalence, we need to be careful about the context in which, the physical context in which we are operating. Okay. Now, a minimum requirement for physical equivalence, seems to me, is that the physically equivalent representations must preserve the empirical content of quantum theories. Okay, that seems reasonable, except that it raises the question, what is the empirical content then? And so, as we saw before, by definition, a symmetry is supposed to preserve all expectation values. And we also saw that by Wigner theorem, a symmetry is supposed to preserve transition probabilities. Nevertheless, in the case of a broken symmetry, not all expectation values computed in the ground state are preserved. Okay? We can in fact find some element of the algebra for which omega x is different than omega prime x. So that's the sense of a symmetry being broken. So why should one deny, as Baker does, statement 2, that physical equivalence implies unitary equivalence? Why should that be possible for physical equivalence to hold without unitary equivalence? Well, I believe, although it's not explicitly that the reason ought to be found in the Baker-Alberson idea that if the empirical content is fully captured by transition probabilities, then by the theorem expressed before, unitary equivalence is not necessary for physical equivalence. W-Unitary Equivalence make it. So if we make this assumption, this big if, okay, and so we think that all the empirical content of the theory is captured by transition probability, then the Baker's proposal might hold. But does it really hold? Let's think back at the concrete case of the magnetization of a ferromagnet. We got two states, omega plus and omega minus. So we can ask questions such that actually cast us on this proposal. These are rhetorical questions, really. Other representations, pi prime and pi minus, physically equivalence just because transition probabilities are preserved under the broken symmetry that flips one to the other? Is it just because the transition probabilities here will be equal to the transition probabilities here that these two guys are physically, or these states and the corresponding representations are physically equivalent? And more in general, is that true that the presence of asymmetry preserving transition probability is sufficient to assure physical equivalence even when the symmetry is broken? I think it's a bit hard to maintain this proposal. And in particular, it's really hard to maintain the idea that the empirical content of quantum theories is fully captured by transition probabilities. Baker is sort of silent on this point. Instead, he suggests that we should drop statement 2 because he really believes that statement 1 should hold. Namely that, and so that's the only way out of the dilemma according to him. He really believes that the presence of asymmetry implies physical equivalence. Here's the quote. One sufficient condition for physical equivalence, it seems to me, but not to me, that is the existence of a symmetry mapping between representations. So according to Dave, notwithstanding the fact that we have spontaneous symmetry breaking in the infinite spin chain, the two representations pi prime and pi minus must be physically equivalent. Why so? Because he claims that orthodox ontologies for quantum theory, let's forget, don't worry about liberalism, what the syllable is here, but he believes that any good ontology for quantum theory should permit a translation between representations if the two representations are physically equivalent, at pain of infringing on the classical notion of space-time symmetries. And I'll come back to this in the next slide. And the intertranslatability, according to him, is assured by the existence of the Wigner unitary W. Now, why does he believe that intertranslatability and therefore physical equivalence should hold between the representations pi prime and pi minus, unless one violates the classical notion of space-time symmetries? Well, that's because, his motivation, his underlying motivation, is this metaphysical principle captured by the condition no primitive identity. So according to him, any ontology of space-time, substantivalism or relationism, in the example he uses when discussing classical symmetries, requires that global space-time symmetries cannot relate different physical possibilities. In fact, these transformations are not, in his view, real physical changes of a system, but just changes of coordinates. And so no primitive identity is the idea that if we have two space-time points, say x and x prime, that are connected by the space-time symmetry, then the corresponding states, omega x and omega x prime, must represent one and the same physical state. They're different mathematical representation, but they're the same state. And he uses the example of the Mexican hat in classical theory. The idea is that, well, I don't know if I can draw a Mexican hat. Can I? Yeah. I know it looks more of a bell chain, but okay. You drop a ball from the top of the Mexican hat, and it will land in any of these possible ground states at the bottom of the hat. Okay, say x and x prime. Okay. Now he thinks that since no primitive identity holds, so x and x prime cannot be physically distinguished from the other, okay, they should all be considered one of the same state. That's because we can connect them by means of, say, a rotation. Okay? Now, I think this point is questionable. Chris knows more about space-time than me. There's a huge literature. Karl Hofer wrote about that. So, not going to question non-primitive identity. Later on in the paper, in the talk, I will question the application of non-primitive identity to the specific case of the magnetization of ferromagnet. But that's the idea underlying the maintenance of statement 1, okay? In Baker's proposal. Okay? So this implies in particular that mathematically distinct ground states, such as omega plus and omega minus in a ferromagnet, must be physically equivalent. Otherwise, he claims, no primitive identity will be violated. So he writes, we might hope that sensible ontologies for quantum theory would at least permit us to translate between the minus Z polarized state and the plus Z polarized state. Now, I contend instead that whether or not two representations pi and pi prime are physically equivalent depends on the type of physical states that the corresponding ground states omega and omega prime are supposed to represent. So the adjudication of physical equivalence really depends on the particular context we're dealing with. And in the case of quantum statistical mechanics, so in the case of the ferromagnet, omega plus and omega minus represent distinct thermodynamical phases, one in which all spins are up, one in which all spins are down. And in this sense, they must be considered physically equivalent because they are two different thermodynamical phases, two different physical states. And I offer two reasons in the remaining part of the talk to support my claim. Let me sketch the idea now and then zoom in the following slides. Omega plus and omega minus are both equilibrium Gibbs states at the same temperature, inverse temperature beta, but they turn out to be disjoint states, disjoint in a technical sense that capture physical inequivalence that I will explain later on. And in fact, they are distinct phases. They cannot be considered the same phase. Furthermore, we can put them together so as to form a mixed state, meaning that both phases are present at the same time. The coexistence of phases is exactly analogous to what happens in the phase transition of H2O from the solid state, ice, to the liquid state, water. 0 degrees Celsius, we can have, light pressure, we can have both ice and water present, but they are different phases of matter, different states of matter. Okay, and this is exactly what can happen also for omega plus and omega minus. Okay. Okay, so let me first tell you in what sense, and it gets a bit technical, but I try to simplify things. First tell you in what sense omega plus and omega minus are thought of in the literature, so there's agreement on that, as thermodynamical phases. And then I'll tell you why they ought to be distinct and why they can coexist. Okay? Now, in quantum statistical mechanics, a thermodynamical phase is represented by an equilibrium Gibbs state, okay, whose matrix has this form. Never mind about that. And in the Gibbs state, macro properties such as magnetizations are dispersion free. So some of their eigenvalues are assigned probability 1 by the states, by the Gibbs state in particular. Now it is known that in the finite case, the Gibbs state turns out to be unique for a fixed inverse temperature, which means that there cannot be multiple phases, which means that there cannot be symmetry breaking, because there's only one equilibrium state. So as I explained to you at the beginning of the talk, in order to have symmetry breaking, we need to take infinite quantum statistical mechanics. And that, for any fixed inverse temperature beta, we can define a convex set, K beta, also called KMS-states. And this convex set is not a singleton, that is, it contains more than one element. And it turns out that the extremal states in this convex set correspond to equilibrium Gibbs states, so better generalize the idea of Gibbs states. And I tell you in what sense in the next slide. But here's the definition of a KMS state. We don't need to go through it now. Just keep in mind that one thing, that the KMS state is defined with respect to the one parameter automorphism group sigma t that defines the dynamics or the time evolution of the system. Okay? So, what are extremal states? Extremal states are of this set K beta are those states that cannot be written as a convex combination of other states, usual definition. And extremal states are actually factor states, so they are figurated algebra at trivial center. So the center of the algebra is just a convex multiple of the identity, and as such, extremal states are dispersion-free, assign dispersion-free values to macro properties, just as the Gibbs state. And in this sense, they're the generalization of Gibbs states or equilibrium states, and therefore the generalized concept of thermodynamical phases. Okay? So in particular, in the infinite spin chain, okay, we can consider the state omega that depends on the external magnetic field and the temperature beta. It's defined as we did before over the quasi-local algebra. And so when we let beta, so when we let B go to zero, the external field becomes null. It turns out that the state omega at zero magnetic field for the given inverse temperature beta induces an automorphism group, what I said before that defines the KMS state, such that when we are above the critical inverse temperature, the convex set is not a singleton, so it contains more than one element, as we want. And in fact, in this sense, the state omega plus for spins up and the state omega minus for spins down are the extremal state of this convex set, and as such they represent thermodynamical phases generalizing Gibbs equilibrium state. Okay. Now, we learned that omega plus and omega minus are thermodynamical phases. Now we will see that they are actually distinct phases and they must be considered as empirically distinct. Now recall that given a state omega, the volume of the state omega is the set of states that can be expressed as density matrices in the GNS representation of omega. So each state in the volume of omega is then possible with respect to omega. That's the idea, the conceptual idea behind the definition of volume. It contains all the states that are possible with respect to the given state omega. And as a matter of fact, the volume of omega plus and the volume of omega minus has empty intersection. So there are no common state. In particular, omega minus does not sit in the volume of omega plus and vice versa. So there is no state that is possible with respect to one, it is also possible with respect to the other. So we say in this condition O that the states are disjoint factor states, and these joint factor states are impossible relative to each other. You either have one or the other, they cannot be physically the same. More to the point, if we define the magnetization observable in the limit for the infinite spin chain, then we can define the magnetization observable for the spin up in the affiliated algebra of pipeline, of omega plus, and the magnetization observable for spins down in the affiliated algebra of omega minus. And as it turns out, these two observables are different. So the value, which means that the value of the magnetization observable for any state in the volume of omega plus is different than the value it takes in any state of the volume of omega minus. And so the thermodynamical phases, omega plus and omega minus, are empirically distinct. They represent empirically different states. They cannot be physically equivalent. Now the second reason why these states are physically equivalent, are not physically equivalent, is that they can be put together to form a mixture, a state omega zero of this form. And if we take this state and we build this representation, okay, we can find projections P plus and P minus in its affiliated algebra that enable us to construct separately omega plus and omega minus, starting from the mixed state. Okay? So the mixed state being physically significant, so representing the coexistence of two states, the two phases, demonstrate that the two states can be present at the same time, just as water and ice. Water and ice are physically different, and so the corresponding representations must be physically equivalent, notwithstanding the fact that they are connected by the flip-flop symmetry. So Pace Baker, I believe, based on this reason, that it is statement one that should be dropped, at least in the case of the ferromagnet. Maybe in either case it holds, but in this specific case that he himself considered, the presence of a symmetry does not imply physical equivalence. And so that's the way out of the dilemma in this specific case. But before concluding, there's one last thing that we need to address. Recall that the motivation for holding statement one, for Baker at least, was no primitive identity. So what about no primitive identity? Does it hold? Is it violated? Does it make sense in this context? And here I claim that the fact that the two phases of the infinite spins chain correspond to distinct physical states does not violate this metaphysical principle, just because the flip-flop symmetries that map one state into the other is not at all a space-time transformation. Why not? Well, because perhaps contrary to quantum field theory, where there is an underlying manifold, space-time manifold, in quantum statistical mechanics, we have no direct connection with space-time. The quasi-local algebra describing the spin chain is defined just over the Euclidean three-dimensional space R3, and the temporal dimension is actually added independently, okay, by means of the one-parameter group alpha t, dictating the dynamics of the system. Moreover, the type of symmetries that exist or that characterize the lattice of the spin chain are translations. And by the covariance action that in quantum field theory, for instance, is captured by the idea that there is invariance under the Poincare group, in quantum statistical mechanics just tell us that there is invariance under translations. So omega plus and omega minus, okay, remains invariance under the action of these translations. And that's different from the flip-flop symmetry. Let's go back to the picture here. Okay. There is invariance under the covariance action tells us that there is invariance under translations. That is, if I map this guy into this, if I translate, okay, this state describing or spins up remain invariant, is not changed, or the state describing spin down remain invariant under translations. Okay. All the flip-flop symmetry does is to fix a point and move it up or down. And look at the orientation of the spin. It's either up or down. There's nothing like doing a rotation of the space-time translation as in this case. Okay? We don't move from one point to the other. It's just something like this type of rotation. It's not a space-time transformation. That's why no primitive identity is now violated, independently of whether or not buying to it as a metaphysical principle to be accepted. So, conclusion, just to resume, even though I criticize Dave Baker's proposal, I believe that this dilemma raises important questions concerning symmetry, unitary equivalence, and physical equivalence, especially in the case of broken symmetries. However, while the relations between symmetry and unitary equivalence in general can be established on a formal level just by the mathematics, in order to settle questions about physical equivalence, we need to proceed on a case-by-case basis. So in particular, in quantum statistical mechanics, ground states, omega plus and omega minus, correspond to empirically distinct thermodynamical phases that can even coexist. And therefore, the representations ought to be regarded as physically inequivalent. So the takeaway message, the moral, the talk is that the presence of a symmetry, especially in the case in which it is a broken symmetries, is not at all sufficient to guarantee physical equivalence. Thanks.
Okay, so you went on a little bit long. We have about
Oh, sorry.
It's okay. We have about 20 minutes for Q&A.
Oh, it took longer than I thought.
Yeah, who would like to?
Just out of curiosity, this goes way beyond that. So, but so it seems. So, if I understood correctly, right? So the thought is here. So the weak unitary equivalence is enough to preserve transition probabilities, right? If you actually believe that the empirical content of the theory is exhausted by them, then you're gonna have that. Physical equivalence does not require, as a matter of fact, a symmetry because the weak, right? So, but that claim of itself, right? The transition probability are enough to. That seems so weird to me.
Yeah, that's why they're
right. So in some other quantum context, like so take the discussion on the identically discernible in quantum mechanics, right? All these people proving that was falsified, right? The first thing that they do is say, to actually be sure that they are qualitatively the same, right? We're going to prove that all the expectation values are going to be the same thing for both the entanglement particles. So and then by contraposing that, if you don't have the same expectation values, I guess these guys have in mind that these are not. They're not qualitatively the same, and therefore, preserving the expectation values should be part and parcel of some minimal form of
right.
Right. I mean that's my intuition too. I mean, if you don't preserve expectation values, how can you claim?
Right. Yeah.
And there are discussions in the quantum literature that actually goes in that.
Yeah. And in a broken symmetry, as I point out here,
exactly. So,
expectation values are not preserved when they are computed in the ground state, because that's the very idea of broken symmetries. So perhaps the underlying idea of Baker seems to be, and in the paper with others, they do some, suggest some, sketch some discussion in the case of quantum field theory. Well, in that case, they claim, well, the vacuum, there are different vacuums, there are infinitely many different inequivalent representations of quantum field theory, and for each of these representations there is a different vacuum. Okay? And then it is true that in case of quantum field theory you can sit in either one of the representations. These representations, so to speak, they don't talk to each other. Okay? And all that matters there, one might say, is that going from one representation to the other, transition probabilities are preserved. But that's in the case of quantum field theory, and this claim is questionable even there. But perhaps in that case you can bind that move. Where you certainly can't, I believe, in the case of quantum statistical mechanics, exactly because this condition fails. Yeah. And there, we're not talking about the vacuum being represented differently in different representations. You're talking about two different guys. It's omega plus and omega minus.
So I have a question.
Yep.
I think at a crucial point in our argument, you rely on the fact that the two ground states have a different magnetization observables. There's the empirical content comes apart from that.
Yeah, well, it's one of the reasons. Yeah.
That's the reason why they're disjoint.
Yeah.
Like
That's what happens. They are disjoint, and because they're disjoint, because they're disjoint, what happens is that if you look at and you define the magnetization observable in the affiliated algebra, then for omega plus and omega minus in their sub-representations, if you want, this guy will be different. In fact, take any state in the volume of omega plus, it will return the same value for the magnetization observable, but that plus 1. But that value will be different for any other state in the volume of omega minus, where the value is in fact minus 1.
Okay. But
yeah, I see.
I can see that this true.
Right.
I can see that there's a case to be made that there are two things, because it could go that way or that way. But I'm not sure whether it's quite right to think of them as empirically distinct, because there seems to be still the situation is symmetrical insofar as whether one of them is going to come out as +1 or -1 really depends on whether I measured magnetization this way or that way, as it were. You see what I mean? It's sort of whether it's one or the other depends on something external to the system which defines which direction is up in a way.
Okay, I take it that the choice of up and down is perhaps arbitrary. I can call up what you call down, but the distinction between up and down is not. So I can call.
I think the distinction is that the fact that there are two, that I grant, but still there's a symmetry between the two cases.
Yeah.
Which one is up, which one is down, is a conventional or sort of external matter. Right?
Yeah. Okay, I buy into that. But still, once the convention is in place,
then
the
they
two guys
yes,
are distinct.
yes,
And
yes.
if I choose the other
That's
convention, they're still distinct.
That's true.
And that's,
that is right.
I
yes.
think, all it matters for making the argument to the effect that they are
Okay.
physically
Yes,
distinct
yes.
phases.
Right. Yes. Yes. Yes.
I think.
Good. Good.
Yeah.
Yes.
So this might seem a facetious question, not a serious one, but the crucial philosophical assumption here is the no primitive identity assumption.
For Baker, yeah, but
From which you derive the idea that if you have a symmetry, then you have physical equivalence.
yeah, that's what he claims. Yeah.
My question is just why believe that? I mean, it's
then you have to
obviously wrong.
Yeah.
I mean,
Well, you
I have trouble, following the rest because, of course, you have primitive identity. I mean, you get the example of the Mexican hat, and since obviously the particle is there, or it is in different places, that's not the same scenario.
Well, I mean, my intuition goes along the same lines as yours. But I was more interested here in assessing, when I started this project on spontaneous symmetry breaking, more interested in understanding the sense in which symmetries might be related with physical equivalence or inequivalence. And exactly because I don't think that the flip-flop symmetry is a space-time symmetry, even if one buys into Baker's view that no primitive identity is a metaphysical principle to accept, the claim that the presence of a symmetry implies physical equivalence does not hold. But I also have doubts about no primitive identity. I'm not an expert of space-time theories, I should say, so I wonder whether there's something deeper behind Baker's view.
Thing that comes from space-time theories that justifies no primitive identity in that case.
It's a contention
But
matter. Yeah.
Let's say you want to prove something stronger, so independently of this, it doesn't.
Yeah.
But it seems that also in this case, I'm not sure I follow what the debate is, but it seems to be just people that have different intuition. They say, well, if I just put it here or there, it's the same thing, and because
Yeah.
it's not different, you have to change it.
Yeah. So, I mean, as I said, I presented this reading, the Mexican hat. I'm not persuaded, but again, perhaps experts in this field can maybe agree with Baker. Maybe there's some more subtle issues or arguments that I don't see, but
it's like some technical or something about the mathematical, the formalism of the theory that goes in this direction. These are just brute intuitions.
I think they throw there a brute intuition, and it does. In fact, he's talking about classical space-time, and then from there, he tries to generalize to any quantum symmetry. So this passage is not spelled out in the paper. I don't see how it could go. But again, independently of whether one can do that, it seems to me that the argument based on no primitive identity doesn't make anything to the claim that the symmetry should be enough for physical equivalence. I think
So,
but maybe
imagine a world which is only populated by a Mexican hat and a little particle or whatever ball on top of that Mexican hat. Now, in that world, at some point, this ball rolls down into this location, or I suppose it could roll down in that position in different ways. Now, the question is, are these two different worlds in a way? Are these two different outcomes, two different physical situations? And I think to the answer to that question depends on how you think about the metaphysics of space. Whether that there is a difference, there is a fact of the matter that somehow it ended up in this spatial location rather than in that, or whether you think no, it's if you're sort of more of a relationalist inclination, perhaps, then you might be saying, look, you might be tempted to think these are different physical situations, but in fact they're not. Unless you introduce additional things into the world, like an observer who's looking at the Mexican hat from one particular point, and then you can say, now it's different whether the ball rolls down right in front of my eyes or towards the back of the hat, or but unless you have any other sort of fiducial point or reference frame that's physically justified, it's just not a difference. I think so. This is
also, let's say, the behind the no primitive entity.
Probably that's and I've certainly seen ideas like that being articulated and defended in the metaphysics of or philosophy of physics of space-time literature. Sort of in that camp, in that tradition, yes.
But in your scenario, there isn't really the full Mexican hat, or it seems it's already big enough to define some.
So if the Mexican had a set of points, space-time.
Well, maybe the bottom or the circle at the bottom.
I think this is the answer will depend on how exactly we think about what the Mexican hat is and what space is and things like that. But depending on how you answer these questions, maybe you might be tempted to say there is no physical difference between these two worlds, as it were, and therefore there should be considered physically equivalent. Something like that. That's the sense in which you dismiss the primitive identity of space-time locations or spatial locations, or maybe points in the whatever this is called, the rim of the hat, or they're not intrinsically primitively distinct somehow. They're really only made distinct by if you add some additional structure. I think that something like this is
going on.
Is the motivation for the principle.
But then what would that make in this case? I still, don't see what the connection will be. Why that might make an argument, even by analogy, to the flip-flop symmetry. I can see. As we were discussing before, it's a conventional choice what is up and what is down. So, again, if it's externally,
right.
The Mexican had
sure,
one.
Yeah, but I think the intuition there is that unless you've added additional external structure to the system, there's no physical difference between a world in which there is an infinite, ferromagnet like that with all spins down, and the world in which, there is that same system with all the spins up. That must be the intuition.
That yes.
Physical difference between these two situations.
It's just that. But then the fact that I can combine these two states to form a mixed state, which is something, by the way, that I can't do in quantum field theory. We were discussing before the example. Doesn't make water and ice. I can call water the solid state and ice the liquid state conventionally.
It's not just about terms you choose to label this. It's not just about the term up or down. It's sort of the intrinsic nature of the physical state is really supposed to be the same, I suppose. But I completely agree with you. The second argument that you can actually form mixtures of the two, that's
more a knockdown. It's a stronger argument.
yeah, that's a very strong argument against thinking about it in this way, I think.
Okay.
Absolutely. I have a question on that other slide, in the same slide I asked you about before, and you say that the disjoint states are impossible with respect to one another, or relative to one another.
Oops.
And so what does that mean? What does it mean to say one state is impossible?
It means that, so the idea is that, remember, the volume of omega is the set of states that can be expressed as density metrics, so they can be written down.
Oh, I see.
In the GNS representation of omega. So if phi is not in the volume, then it's impossible with respect to omega. And so it turns out that not only omega plus is not in the volume of omega minus and vice versa, but there is no state in the volume of omega plus which is also in the volume omega minus. So there is no state possible with respect to omega plus which is also possible with respect to omega minus. So it's even stronger than saying, well, omega minus is not in the volume of omega plus. There is no state expressible in terms of omega minus possible. That is yeah, that's it. Yeah.
It's a quarter to. Maybe one of you has an urgent question? No? So please join me in thanking Giovanni.
Yeah, thank you.